This conference will now be recorded.
Hello, everybody. Jordan Girth here from the National Weather Service Office of Observations. Thank you for joining us for the Satellite Book Club Seminar Series. This is session number 93. Hope your spring is off to a good start. It's been some active weather across the central part of the country. Past 2 days looks like that is calming down. Today's presentation, how GLM lightning observations can explain aircraft flight paths during thunderstorm events. Our presenter, Joseph Patton, Assistant Research Scientist with the Cooperative Institute for Satellite Earth System Studies at the University of Maryland, College Park. The facilitator for today is Brian Curran, the Sioux from the Midland, Texas Weather Forecast Office. As you just heard, this session is being recorded. There will be an opportunity for Q&A after the presentation. We're particularly interested in questions from field offices and regional headquarters. So please put your question in the chat room and we will field them there. Also, we encourage you to sign in with your full name or specify your full name when asking a question in the chat. That will allow us to get back in touch with you if we need to. We're always looking for future presenters. So if you have an application you'd like to share with your colleagues, please get in touch with the TowerS team. We'd love to have you be part of a future book club. And for training materials that you may be unaware of or may be unavailable, Brian Mott at the Office of the Chief Learning Officer can help with that. I'd like to thank the TowerS team, Kashad Bowman, the Office of the Chief Learning Officer, GOZAR JPSS program, our facilitator, and you for your support of the Satellite Book Club. Today, Joseph Patton is an assistant research scientist with the Cooperative Institute for Satellite Earth System Studies at University of Maryland, College Park, focusing on lightning research and training. His current position involves studying operational forecasting techniques using the GLM and creating training materials based on lightning information from the GLM for forecasters in the Western Hemisphere. Joseph graduated from the University of Oklahoma with a bachelor's in meteorology and Florida State University in 2017 with a master's. Served as an operational meteorologist with the Weather Service in Goodland, Kansas before joining CISESS in the DC Metro. We're glad to have Joseph back to the Satellite Book Club. Welcome.
Thank you so much. Very happy to be back. It's a pleasure always to be here. So as you've done in your wonderful introduction, you've laid out that we're going to be talking a little bit about GLM gridded imagery and how that appears to affect those aircraft flight paths. So please advance to the next slide. So just to set up a little bit about what we're talking about today, we want to focus in on that thunderstorm activity because we know that flight paths are so greatly impacted by those ongoing thunderstorms. Obviously, safety is the number one concern of the pilots and the airlines, and in order to protect the aircraft and ensure the safety of the passengers and crew, they're going to avoid those turbulent updrafts and downdrafts. And in doing so, that incurs economic costs of increased fuel consumption, increased fuel storage, additional labor costs from everywhere from the gate agents to the pilots, and those delays in general can be significant. We are going to investigate how it appears that convective initiation and convective mode may play a key role in explaining aircraft course and how and when they choose to divert their path. So next slide. Here's the first case study we're going to be looking at today. And just to get your feet wet with this particular day, this is from May 17th, 2019. And we're going to be focusing on that convection that's occurring over Kansas and Nebraska. With this water vapor imagery, we can see that strong storms were developing in the central portion of these states, but also there were some storms developing along a visible dry line where we can see those yellow shades of drier air advancing from eastern Colorado into western Kansas. The orientation of the shear vector that day favored discrete convection, which we see is what was firing, especially along that dry line. And as such, this was sort of an all hazards event where tornadoes, wind, hail, flooding could all be a concern. Next slide. So this is our first look. We're zoomed in a little bit to that tri-state area with northwest Kansas, northeast Colorado, and extreme southwest Nebraska. And this is the ACARS flight data. It's labeled here as ACARS, but it includes ACARS and slightly more registered aircraft who aren't technically part of the ACARS system. But this database is actually stewarded by INSEP, and it's an archive database of most of the headings and locations of registered aircraft as they're reporting, and it includes almost all of that ACARS data. And so this is being plotted here in real time with the 1-minute mesoscale imagery from the GOES 16 channel 13 ABI long wave infrared. And just watching this without any other context, it's kind of hard to tell exactly where planes may be avoiding certain convection. Like it clearly looks like they're avoiding the storms in general, but you also see times where it looks like they appear to fly right over some of the colder cloud tops, and there's not really an exact specification as to which ones they're avoiding, which ones they're not. But we know that in general, they're going to tend to avoid those areas closer to the turbulent updrafts as opposed to those ample regions. Next slide. So now we're showing the same aircraft data, but we've switched the imagery that we're looking at a little bit. So we're focusing in on the moment up until convective initiation, which we're seeing for that discrete storm along the dry line in northwest Kansas. So for this scenario, what we've plotted here is a day microphysics RGB, similar to a day cloud phase distinction, but not quite the same. But it shows similar cloud microphysics in that when those robust turrets of red pixels start showing up, that's indicating ice developing at the top of the cloud along that dry line. So advance. And NWS Goodland noted about in their update at 1919Z that that microphysics RGB had indicated a few failed attempts at thunderstorm initiation along the dry line, and they expected storms to fire between 2 and 3 p.m. And sure enough, about an hour later, that's when they occurred. Now, one thing I do want to point out here is that the GLM FED very quickly captured that convective initiation because there was relatively little things to block the signal, to block the optical signal from the lightning strike to the instrument itself. So it had a very direct view of this isolated discrete storm, and it was able to quickly detect those first lightning strikes right at convective initiation. And that's one of the powerful aspects of the GLM, is that you get this spatial extent and you can see that convective initiation really early. So next slide. Next. Thank you. So this one, it's the same imagery, but we're going to look through convective initiation to the event. And I just want to kind of give you a moment to take in, look at where these planes are going, how they're avoiding certain lightning strikes. You know, the GLM shows you the spatial extent. All the gridded products do. That's one of the universal characteristics of the GLM gridded products, is that they give you the spatial extent of lightning, which you don't necessarily get from just plotting the points of centroids of lightning strikes. And in addition, flash extent density tells you where are you getting the most number of flashes, or where are you getting a relatively higher number of flashes. And we can generally see from this imagery that it appears that those convective cores have those warmer colors of flash extent density, right? Those lighter blues as opposed to those darker blues, lesser flashes, lighter blues and yellows, more flashes. But with this particular case, it's kind of a low flash rate, right? So it may not necessarily be easy to tell from this specific GLM gridded product exactly which lightning strikes the pilots are trying to avoid and would want to avoid because they're more associated with the updraft. So we can switch this up by looking at a different GLM gridded product. So let's go to the next slide. Oh, sorry, let's read this for a second. So NWS Goodland, this is part of their forecast update from earlier. So they did say that the LCLs were relatively high on this day, and there was weak 0 to 1 kilometer shear support, or shear, and that supports the initial threats being very large hail greater than 2 inches in diameter. And they mentioned that the tornado threat was somewhat low, but that would increase as the storms cross the Nebraska border and the low-level jet increased towards the evening hours. So next slide. So now we're looking at the event from the perspective of minimum flash area, which is a different JLM gridded product. And instead of focusing in on the number of flashes, all we're doing is looking at which flash, where are the smallest flashes occurring? And within those small regions where the smallest flashes are occurring, those flashes are more likely to be associated with the updraft for 2 reasons. One, because you have a lot of charge separation happening within a small spatial area in the updraft, and that allows for those flashes to happen over a smaller spatial extent. In addition, the nature of the updraft itself is that it's vertically oriented. So if you're looking from a satellite down on it, and you're seeing a column of flashes all happening in a small spatial extent like you do with an updraft, they're going to appear spatially small to the instrument. And that's what we see stand out with the minimum flash area. Those updrafts pop out with those gold pixels in the minimum flash area product. And those strong updrafts, which can be quite turbulent and quite hazardous for pilots, they may also introduce icing conditions, which would not be very good for the aerodynamics of the aircraft. All of those things make the minimum flash area product quite valuable at telling where aircraft might be avoiding certain flashes as opposed to other flashes, especially for a low flash count event like this. So as we look through the minimum flash area, we can see that there's a large amount of traffic going through that central US flight corridors that is very much disrupted as this complex of storms is developing. Those orange polygons that you see plotted are SIGMET advisories from the NWS CWSU. So don't let those throw you through a loop. I'm just plotting them to kind of get more of like an aviation perspective of what a WFO forecaster might call a severe thunderstorm warning, for example. It's just something the pilots might want to avoid as they're going through their traffic. And sometimes it's co-located with convective activity. Sometimes it's more related to turbulence. And we'll see a little bit more about that in this next case. But just to get our feet wet here, we're just seeing how those pilots are interacting with the lightning activity going on around them. And then also seeing the added context that different GLM products can provide when looking at how those numbers vary, especially for these low flash count events. So go to the next slide. Oh, yeah, so that pretty much sums up about the air traffic and those east-west flight corridors. You know, they were really they're flying around that developing convection. And then as we got towards the later hours and it became more of a complex of storms, you see more traffic just really being diverted around the whole thing. Next slide. So here we'll see this image will flip back and forth between sort of an early event and a late event time frame. And you can see the difference in all the air traffic. So much of the air traffic that was spread out between the Dakotas and Nebraska and even into the Oklahoma Panhandle is now all being squished into sort of 2 regions, you know, arching over, you know, say north from Minneapolis or south into the Kansas region as the storms have already moved north into Nebraska. So you can imagine that all of this is adding flight time, all of this is adding fuel costs to the airline, it's adding delays to the passengers who themselves incur a hidden economic cost, which is not counted in all of this. So, you know, some of the things to hit home from here are the spatial extent of lightning from the GLM products really aligns well with those aircraft flight paths. And when we can identify those stronger convective updrafts with the GLM, where we see more numerous and also smaller minimum flash area flashes, that may provide additional insight into specifically those turbulent areas which the pilots are trying to avoid. So next slide. So now we're going to look at a second case study with a more organized convective system. And I think that we will see just how much of an effect that can have over thousands of miles. So in this particular case, this is from a derecho which happened in December 2021 across the Midwest United States, starting in the sort of central Great Plains region and then moving eastward into Iowa and Wisconsin and Illinois. So the convective mode here suggests damaging winds is the #1 threat, followed closely by QLCS tornadoes, which ended up being realized with several significant tornadoes being observed on this day. So just to get our feet wet with what this case looks like, this imagery here is just radar reflectivity mosaic from that day with some of the severe reports and NWS warnings. The strong dynamics within the large convective system obviously would be very difficult to fly through. So you can imagine that there aren't going to be a lot of people who are just going to brave it on that one. And we've got a really populated flight corridor. So let's see what that looks like. Go to the next slide. Thank you. Next. So first of all, that's a map of our corridor of where the severe reports come from. Next slide. And NWS Omaha noted that wind gusts were expected to be on the order of 60 to 75 miles per hour in the afternoon. And they were expecting a strong westerly sting jet to develop, wrapping around that dry conveyor belt. And they were expecting widespread damage, not just from the storms, but just from the strength of the jet within the convective system itself. Next. So here are the aircraft flight paths with flash extent density and just the NWS WFO warnings from that day, convective warnings from that day. And I've plotted here the trailing aspect. So it's the last 5 minutes, and it sort of trails off in opacity. So you get a stronger jet, a stronger line towards the beginning of the time. And you can really see how those planes are diverting their flight path to get around this strong convective system. We see at the beginning a very large amount of pretty much east-west traffic. And as this large convective system develops and progresses eastward, we see a very large amount of traffic not wanting to brave these strong convective updrafts. A few of them do, we'll get into why, but you see a very large amount of traffic being diverted around south. And then as soon as they get around it back up north, because maybe they're going to the Pacific Northwest or the Intermountain West, or even Northern California, and it would make more sense for them to come back up as they have to be diverted southward around this convective system. So the really interesting thing here is you can see those really busy airports like O'Hare and St. Louis and Kansas City, all having to sort of divert their traffic. Sometimes we see planes will come in on the backside of the derecho and kind of hang out for a few minutes and wait for it till it's safe to land, and then they'll land. So they're really just circling to maybe avoid some of those conditions. If they can wait 10 minutes, then maybe the storm will pass by. So that's something interesting we can see from this as well. But I think there's a little bit more context to be seen with the other GLM graded products. So next slide. All right, so before we move on, I did want to note that NWS Omaha, a wonderful forecast discussion from them, said at the end of, towards the end of their short-term discussion, said to put the system in context, the large majority of fields available, such as surface temperatures, sustained winds, and gusts, are at the very top of the ECMWF model reanalysis for this time of year, going back 20 years. So they really wanted to hit home that this was an extreme system, and it ended up producing multiple significant tornadoes, several wind gusts that were measured over 80 miles per hour, at least one that was measured over 90 miles per hour. So definitely nothing to sneer at, especially for December, right? We're talking about a little more than a week before Christmas. So it makes this definitely an interesting out of season event. Next slide. So here we're going to look at that same event, but instead of plotting flash extent density from the GLM, we're plotting a minimum flash area from the GLM. And instead of plotting the WFO warnings, we're plotting those SIGMET advisories. So now we can see a large amount of SIGMET advisories highlighting all those areas where we see that large convective system developing We can almost see that bookend vortex up in Minnesota as well. And it's basically telling all these pilots, like, don't fly here if you don't have to. Avoid it. You know, there's more details in the product about what exactly the hazard is, just like there would be with a severe thunderstorm warning. But visually, this is supposed to convey the message that this is an area that pilots in general would not want to fly through if they have the opportunity not to. So in this particular case, it really highlights the entire convective system of the derecho. We don't see that much added context in terms of where the pilots are trying to avoid. Obviously, some of them are flying right through it as they are able or as they deem it necessary. But one thing we can look at in more context, I think, is if we just look at all of the pieces together at the same time, I think we may be able to put them together. And that's how a forecaster would see it, right? A forecaster is not going to look at an hour of flash intensity and an hour of minimum flash share. A forecaster is going to have both of them up on the same panel and be looking eye to eye. So let's look at that, right? So next slide. So as we said, almost all the planes avoid those SIGMAT advisories. The convective lightning tapers off, and planes tend to avoid the lightning, but we'll see more context on the next slide. So here's all three of them together for a time later in the event. I believe this is 23:44 UTC. So we've got radar on the left-hand side. We've got flash density on the middle, and we've got minimum flash area on the right-hand side. And if we compare all of these, we can see that there's the cluster of tornadic activity going on in central Iowa, and that corresponds to the reports that we saw with the SBC report map that we saw a few slides earlier, right? That's where most of the significant tornadoes were occurring, was in that region. And we can see that there's definitely not a lot of flight traffic going through there or around there. But we can also see that what stands out oftentimes is that those convective updrafts have higher amounts of flashes, which we see with those red FED pixels, flash intensity pixels, and they also those convective updrafts are also highlighted by the gold minimum flash area pixels, indicating small minimum flash area sizes, right? We've got those small flashes happening in the convective updrafts. So when we co-locate those areas with the low minimum flash area, the high flash intensity, and the radar returns, that really stands out as specifying where we can see those areas of turbulent updrafts developing, and where we might see some increased chances for severe weather. So obviously from a WFO perspective, that provides value. But in addition, next slide. And next, there you go. In addition, that minimum flash area product specifically shows that aircraft who do brave the trek across this MCS appear to fly along paths which route towards weaker portions of the line, as indicated by those higher minimum flash area values. So they're sort of shooting the gap in the minimum flash area, looking for those pockets of greater flash size, where you got those purple and green pixels as opposed to those yellow pixels, because those flashes are more associated with the turbulent updrafts. And I think it's incredible to see the pilots who are, a lot of them are just seeing and avoiding. I think it's, or they may be more directed by the flight air traffic controllers. But either way, I think it's incredible to see that often lines up with where we see the flashes in the lightning, which are less likely to be associated with those convective updrafts, as identified in the minimum flash area product. So next slide. So we've reached the end. This is just another perspective of that same derecho that we already looked at. The next steps for this, I want to continue creating some formal training documents with this, using examples from GLM imagery with applications for the aviation community. That obviously involves adding additional cases and working with organizations like the Aviation Weather Center to refine and disseminate and store this training material. And then we also want to continue to demonstrate the value of the GLM in operations and for generations to come. So my email there and my Twitter is on there if you want to reach out to me, and I'll be happy to take any questions.
Thank you, Joseph, so much for your talk. Please, folks, stay on for the discussion, and especially those from the field forecast offices and regional HQs. I see we've got a few things in chat now. Brian Mata would like to know if you have any hurricane examples to show.
I have made 2 hurricane examples. I actually made one with Hurricane Laura and one with Hurricane Michael. And as you know, Michael would be early in the lifetime of the GLM observations. And they were very interesting. You could see them very obviously avoiding the hurricane itself. But on the scale of convective systems, they're not that large. So like I think personally, looking at these Midwest cases elucidates a little bit more. But you are right in that those hurricane cases are quite interesting. And I think that they do have a purpose. And we would definitely want to incorporate that, and it's something that we've looked at already. So thank you for the suggestion.
I was remiss if we can go back to the last slide. I'd like to remind people that we do have another talk coming up next Thursday at, I believe, what time? Oh, I'm sorry. I'm looking at. I'm trying to do the math conversions in my head. At 12 p.m. ET, 1700 UTC. That's 11 o'clock for us in Central Time. Bill Line, a physical scientist from NES STAR, will discuss late winter and early spring dust storms, which those of us down here in the Southern High Plains can certainly relate to. If you have any questions for the TowerS team, or if you need configuration of satellite products, the team is available to help. Feel free to reach out to John Evans, and his email is there, john.d.evans at noaa.gov, and Lee Byerly, lee.byerly@noaa.gov for any support. And as always, if you have questions or comments about the TowerS team, about the Satellite Book Club, reach out to Kashad Bowman, kashad.bowman@noaa.gov for some more details. You can also follow us in the NWS chat room, Tower-S. And I'll get back to some of the questions now in the feedback here. We also have a short survey that Tristan has posted onto the chat room. If you have any questions for the survey, the link is there. I'd encourage you to fill that out as you're able. Moving on here, Scott Lindstrom mentions this. Do you know if there's any airlines that have GLM observations in the cockpit? I'm guessing that's not the case due to bandwidth, he says. Are you aware of any, Joseph?
I am not. That would be incredible if someone was. Please let me know, because I would definitely want to be involved. If they have it before I can give it to them, I would be very impressed.
Yeah.
This is Scott Romanski. I have something I could add to that. The FAA has what they call the offshore precipitation capability, and it looks a lot like radar, but it extends way out over the ocean. And that's something that they make available. And I think they've had at least a demonstration where that product was available in the cockpit, and they were able to show an improvement. I think it was on the order of a saving of 10 or 15 minutes in terms of diverting earlier, based on what the pilots had available from that offshore precipitation capability. And so I think that study continues. And so it's not them looking at the gridded products per se, like Joseph was showing, but that information is incorporated with other sets of data as part of that product.
Thank you, Scott.
That'd be real awesome to have, saving fuel. Steve Goodman has a question. He says, for added context on value from lightning, it might be helpful to show radar at 18,000 feet and 30,000 feet to see if radar alone is providing the info for diverting tracks.
Yeah, that's a really good suggestion. Yeah, when you look at a constant altitude plane projection like that, it would definitely sort of indicate more what the pilots would be seeing along a certain flight corridor, right? So yeah, we haven't looked at that yet, but I definitely appreciate the suggestion. That's something that I would be able to create, but it would take a little bit more time. So thank you for that suggestion.
Yeah, thank you, Steve, for that. I'd like to see CAPIs too in our radar data. Thomas Earl has a question about parallax data. Joseph, how do you handle the parallax data like GLM and non-parallax data like radar and air traffic plots?
Yeah, that's a really good question. You know, we've released some training documents about this before. So if you look up some of the GLM quick guides from CIRA, you may see some more training material on this. But the important thing is to be able to visualize as a forecaster as you get further away from the center of the field of view of the instrument. You're going to have to account a little bit more of an offset towards the center of the field of view when you're comparing that to ground-based observations. So, for example, a forecaster in Montana may have to mentally shift the flashes a little bit closer to the field of the center of the field of view of the instrument, right towards the southeast, than say a forecaster in Miami. But that it's important to be able to make that distinction that these are satellite-based observations, right? That these aren't ground-based observations, and that that what you're looking at in terms of that gridded imagery does not have a parallax correction, or it has that the parallax correction has been taken out of it. So in this case, the important thing is to, I think, you know, if you're a forecaster in a specific area, you're going to have, it's going to be static, right? It's not going to be changing all the time unless you're going from, like, say, GOES 16 to GOES 17. Obviously, it'll be different between the two satellites. But usually there's one satellite that's a little bit, at least has a little bit better view, depending, and sometimes depending on the event. But when you're within that satellite, you can sort of mentally say, okay, well, maybe I can shift it a little bit towards the center of the view, center of the field of view of the instrument, just based on how I know that instrument is looking at what's happening from the cloud. And I don't think it's one of those situations where you know, you might get confused, but I do think it's one of those situations where you need to say, okay, well, you're sort of shooting an arrow that's not straight up and down, right? You're shooting an arrow that's going through different layers at different levels. And yeah, I just think it's something that with practice, and the more you see the GLM observations, I think the more you'll be able to relate them to the ground-based observations without being thrown for a loop by that lack of parallax correction.
Thanks, Joseph. Dan Lindsay has a question. He says it was more general to, I believe, Brian Mata's question. He says that he's curious if you have any examples over the open ocean, say with Conus to Hawaii flights, or in the flight corridors in the North Pacific or North Atlantic.
That's a really good question, and it's actually something that I've looked at, but for whatever reason, sorry, this data set is limited to U.S. airspace. So
okay.
I don't have access to flight paths outside, which also made the hurricane case slightly less interesting, because you couldn't see like those transatlantic flights coming across, or you couldn't even see the flights coming up from, say, Mexico. You could only see them as they sort of entered U.S. airspace, and so that was that's a limiting factor within the data set. but it certainly would be interesting to look at. And we've gotten some suggestions at different data sources we can look at to make the same sort of analysis. And that may be something which we're able to put together. So definitely appreciate the suggestion.
Jamie, and I'm sure I'm going to butcher the last name, Ederlin, has a comment. Lightning is typically tied to higher cloud tops, and cloud tops play a big role in aircraft routing. Planes cannot fly over cloud tops at or above 32,000 feet. So I'd be curious to see if GLM data in additional cloud tops. You're correct that aircraft look for any break in the line where they can get through, and the Center Weather Service Units, CWSUs, the Mets there are frequently asked how long controllers can fit aircraft through the gaps you identified. And that's not an easy question to answer. Shooting that gap is could be very problematic for pilots, I would imagine. Wouldn't you think so, Joseph?
Oh, for sure. And I think that's where the intuition and the meteorology still makes its bread and butter, right? Is being able to tell how and where those gaps are going to evolve and whether they're going to be able to be usable to pilots and aviation specialists like the air traffic controllers. And Jamie makes a really good point, and I think that's similar to the what we were talking about earlier with the CAPI, the constant altitude radar applications, right? That would kind of show a similar sort of, okay, yes, they can go up to say 32,000 feet, but then they'd have to go around it, right? It's a mountaintop with a lid on it. So yeah, so that would be really interesting to look at, and I think it's in that same vein. So maybe we can focus as we go forward at looking at some more altitude-based instructions as well.
I'm sorry, Michael. Jamelkowski, I believe is how you would pronounce your last name. Excellent presentation, Joseph. It's important to exemplify the uses and benefits of the GLM, especially as the fledgling GeoXO program decides on their final instrument complement for the next generation set of geostationary systems. And I would certainly wholeheartedly agree with that. Tim Schmidt posts a comment, for what it's worth, the web app on Parallax from Geo from 3 different cloud heights, and he provides a link in chat. And we'll see about getting that into the notes. Steve Goodman has a reference to a paper creating synthetic radar imagery using convolutional neural networks. We'll get that also into the documentation as well. Thanks, Steve. Jordan Girth has a question. In your December 2021 example, why do the CWSU advisories appear to be behind the progression of the line? Maybe I am misunderstanding what those CWSUs are for, or advisories are for, rather.
Yeah, that's a good question. It's sort of hard to reorient yourself around that different product. So is it possible for us to go to that animation in my slide set and make it a little easier to talk about? You can just back out and go towards the end. It's towards the end. Yeah, the second to last one. Yeah, so that's a good point that you see a lot of those CWSU advisories sort of behind the convective line. And the important thing here is to realize what those SIGMET advisories are for. And those advisories, yes, the pilots are trying to avoid the turbulent updrafts, but the SIGMET advisories are, can you go back, please? The SIGMET advisories are meant to identify areas which would be hazardous to pilots to fly through on the time scale of 1 to 2 hours. So something with a little bit longer fuse that would be more actionable to pilots. So one of the things we talked about with this particular example was that there was that strong jet of winds coming in sting jet associated with this convective system, and just the turbulent change in direction of winds itself would be a hazard to pilots, especially as they're changing altitude. And so I think that from the perspective of it's supposed to be a little bit longer term of a product, and considering the additional hazards, the different types of hazards that the pilots in particular would be wanting to avoid, I think that's why you might see a little bit of sort of a discrepancy between where the CWSU polygons are and the actual ongoing convective activity.
Right. I see that Robert LaPlante mentions that the AWC may have issued the convective segments, at which point the CWSUs would no longer need to issue a CWA center weather advisory. So that kind of jives with what you were saying. We're about ready to wrap up here. Unless anyone has any more questions, I will take the liberty of asking the final one. What are some ways, Joseph, in which aviation forecasters could incorporate GLM observations into their routine operations?
Yeah, that's a great question. Thank you, Brian. I think the number one way that stands out, and I think that we covered this in the presentation, is really that identifying those convective updrafts and identifying your developing convective mode and how that correlates to what the hazards are going to be. You know, you're looking at something that's being physical, that's being measured, and the important thing is how can you relate that to your mental image of what that ongoing convective activity is. And it's that mental image that complete mental image which will allow you to make better decisions, especially if you're directing pilots. So I think the important thing here is to realize that GLM is just another tool in the toolbox, and it's to try to help you better understand these convective systems and what their hazards might be.
Awesome job. Awesome. Thank you so much, Joseph, for your presentation. At this point, I guess I'll kick it back over to Jordan for final remarks.
All right, thank you so much for your presentation, Joseph. And once again, thanks, Brian, for your help facilitating our discussion today. I appreciate all of you on the line for being with us. As a reminder, once again, Satellite Book Club continues next week with Bill Line from NESDA Star. Is going to be talking about late winter and early spring dust storms. So hopefully that is topical for everyone. In the meantime, if you have any questions related to configuration of satellite products, you heard it earlier, Tower S team is standing by. With that, hope your spring is going well. Please take care, and I'll see you again next week. Bye now.